In Chapter 11, we'll be looking at an introduction to differential equations and visualizing slope fields. A differential equation is basically just a derivative. Here's a list of derivatives, dy dx forms, and they are representing rates of change of y with respect to x. So some of these differential equations look like they could have come from functions of x. And others look like they came from functions that were in terms of both x and y. All right, so for example, what function would have a derivative of 2? That had to come from a linear function in terms of x, something like y equals 2x. Okay, but what function or curve has a derivative of negative x over y? We might not know the answer to that question at this point in the game, but we're going to look at what's called a slope field, and we'll figure these things out as we go. So instead of looking at classwork for day one, I'm going to have you go to this link. And at this link, you'll be able to generate slope fields. Okay? The only thing you're going to need to use are two boxes. This first one, where you're going to input the differential equation. Once you do that, you can hit make a slope field, and the graph below will show you the slope field. Later on, you can come back and graph a particular solution using this box. And your solution will show up on the curve again if you hit make slope field. So let's go to that site and we're going to take a look. Here we are. We're going to take a look at the first function or differential equation, and I believe it is dy dx equals negative x over y. So I'm going to type in that differential equation. I'm going to hit make the slope field. And I'm going to scroll down a bit so you can see that better. All right, and it appears that we have little slopes representing the slope, or little segments representing the slope at each particular ordered pair on the graph. Okay, so I'm going to go to this picture, all right, and so what's happening is if we let, just to think about how we calculate or how we draw a slope field, if we let x be 1, 1, the point 1, 1, then dy dx would be negative 1 over 1, or negative 1. So at that point on the curve, if we go to 1, 1, it looks like it's about here. There's the little slope that we draw, the little segment that we draw. It has a slope of negative 1. Let's take a look at one more point. If I look at the point negative 3, 2, okay, that means dy dx is equal to negative of a negative 3, so that's a 3 over 2. So that's a slope of a positive 1.5. So at negative 3, positive 2, this slope represents the value, or this segment represents the slope having a value of 3/2. Okay? Notice when you get to x equals 0, where does that happen? That's all along the y-axis. Notice that all along the y-axis, the slopes are in fact horizontal. The segments are horizontal and the slopes are 0. Okay, also notice that when y equals 0, we're going to have undefined slopes. That means vertical slopes. And you'll notice these aren't just tick marks on the grid, they are actually little segments representing vertical slopes. Okay? All right, so that gives you a little indication of how to draw a slope field, although in this first activity we're just going to use the generator. Okay, what do the solution curves look like? All right, so a slope field is a graph of all the slopes for this differential equation, and what it represents is a solution of curves, or a family of curves that are solutions to the differential equation. So if I look at all these slope fields, slopes, it looks like we're just going in a circle. Okay, some circles are smaller, some circles are larger. Okay, but this slope field represents a family of curves that will be the solution to the differential equation. Okay, now I just want to point out that what I drew right here is actually pretty bad. Okay, that is not good slope field drawing. Think of the slope field as a current, water flowing. You want to flow through the current or with the current. Okay, so when you draw a solution, your curve is going to flow within the slope field. You will never draw a slope field where you are actually crossing the little slope segments because you're not following the flow. Okay, so when I say it's kind of bad in this region, it's because it looks like I didn't draw that very well. It looks like I've not gone with the flow of the current. Okay, all right, so these are circles. The slope field represents a family of curves given by the equation. Well, if these are all circles, then the answer to this, if I could solve this differential equation, would be something like x squared plus y squared equals r squared. Okay, I have drawn the particular solution that goes through 2, 0, and the equation of this particular solution would be the circle x squared plus y squared equals 4. Okay, we're going to look at the next slope field. This is not my example, but question number 1. So here, our slope is always -1. All of these little line segments represent a slope of -1. We're supposed to draw a particular solution through the point 1, 3. So let's go find that point, 1, 3. So that's up here. All right, and if my graph must pass through that point, and if my graph must have a slope of -1 the entire time, then here would be a particular solution passing through the point 1, 3. When you draw your curve must be drawn to the edge of the grid. Don't stop halfway through. Okay, and then follow the flow of the slope field, never cross any of the little slope segments. Okay, passing through -2, -2, we must follow the slope, which must be -1. Okay, if you had to think about the function whose derivative was -1, you'd probably say y equals -x plus some constant. Okay, the constant is different for the blue line as opposed to the red line. All right, the next differential equation, here we go, is the differential equation x over y. So remember the last one, or the first example we looked at, was -x over y. Okay, signs are just different. This turned out to be a circle, right? Okay, what is this differential equation going to yield as a family of curves? Okay, it looks like there are some asymptotes on this curve. And these asymptotes are passing through the origin. You might recall that we're looking at a family of hyperbola. Okay? Let's look at the hyperbola that passes through the point 0, 2. So here's 0, 2. We're going to follow the flow of the curve or the slope field. So something like this. All right, but a hyperbola has 2 branches, so there's probably this other one down here. Okay, again, as long as you are not, crossing through the slopes, right? No, that's wrong. Your solution's going to be okay. All right. Okay, if I look at the curve that passes through 3, 0, okay, this is going to be the hyperbola opening left and right. That wasn't too good. I should probably go out here a little bit more. And there's probably a left branch and a right branch. Okay? Remember, if they open up left and right, it's an x squared as the first term minus a y squared. And if they open up and down, it's a y squared minus an x squared. Now, these are very general. There could be other coefficients or values within that equation, but those would be the general equations. Okay? All right, the next slope field says the derivative of y with respect to x is x. Okay, you probably know what function that probably came from. Some form of y equals x squared. Okay, maybe 1/2 x squared plus a constant. Taking the derivative of this would give you a slope of x. Okay, so these general solutions appear to be quadratic in form. If you just said x squared plus c, that's okay. You're getting the gist of what's happening here. Okay, 0, positive 3. Looks like my vertex of this parabola is on the y-axis, and that makes sense because on the y-axis, where x is 0, our slopes are going to be 0. Okay? Through -2, positive 2, our slope, I don't exactly know how it's going to flow, but stay within the slope field current. Make your graph go off the grid. Okay, let's look at another one. dy dx is 2x. Okay, how does this look different from dy dx equals x? Well, it's got steeper slopes to the left and to the right as x's get larger or away from the y-axis. The x equals 0, still along the y-axis we have all zeros. Okay, so still a quadratic. Now I want to take a look at the fact that dy dx equals 2x is in terms of only x. Notice that we have vertical columns of the same slope. Okay, so this will help you later when you start matching functions. If your derivative is in terms of only x, you're going to have vertical columns of the same slope. Okay, I'm going to look ahead. Here we have a derivative in terms of only y. Okay, notice we have horizontal rows of the same slopes. Okay? All right, I'm going to pick it up in the next video.